My topic is about Airy pulse propagation, interaction with a convergent layer, and some analysis of its spectral characteristics. And first of all, I would like to speak about what is Airy pulse. Okay, Airy pulse and Airy beams that can be formed in optics, in radar systems. So mainly is described according to the classical electrodynamics, Maxwell equations, and connected to all systems, to all physics that is generated by electrons and by electromagnetic energy. And these Airy beams, they have some interesting characteristics. First of all, it's self-acceleration and changing direction in while propagating in space. So here it's presented the maximum position of Airy beam, and you can see that it propagates not linearly in the space, but according to some trajectory, almost like so changing in space. And here on this picture, you can see that position of maximum was in point 0, and then it's moved. For example, here we have already lost the maximum position, but here it's moved on some millimeters while propagating on distance in centimeters. And this self-acceleration can be controlled, and it depends on the first function that is connected or that is formed in the 0 position. And this Airy wave packets was founded by Berry and Ballas as a solution of Schrödinger equation in the context of quantum mechanics. And first results in optics, the same results were obtained from Helmholtz equation. And first results, as it usually can be in theoretical calculations, as for example, when we mention model of signals like sine or cosine function, we understand that this function is infinitive. There is no any restrictions on its duration. The same first solutions were obtained on this topic using infinitive Airy function. And you can see here that this is it's Airy pulse. It's represented in time, or it can be also in space. For example, Schrödinger equation, it was solved replacing the coordinate of time into coordinate of space. And here it's square modulus of this pulse. It's just intensity and its propagation in its changing in time or in space. And really, first results I can show you here. This is a picture when we have infinite pulse description at the initial data as initial solution of equations. You see that it does not change amplitude in time because it has infinite energy, because the just this Airy pulse, it's as function cosine or sine, it's infinitive. That's why such pulses, they are also characterized like non-diffractive pulses or non-diffractive Airy beams, self-healing, and also self-healing and self-acceleration. Self-acceleration give us changing the trajectory of propagation in space. Self-healing, it's shown here that while propagating in space, it was simulated that on the way of our Airy pulse, it was used some plate that close it. And after propagation around this plate, or so the main beam was closed here in the beginning of the coordinates, in the beginning of propagation. But after some time, this beam can so it's self-healing. This beam restart it, and this beam increase in space again, and can continue to propagate. And this is situation B. This is characteristic for real pulses, truncated Airy pulses that are used at that are used at the initial data in the solution of Helmholtz equation or Schrödinger equation. So when we have finite this Airy pulse, and amplitude is can be amplitude or time duration can be sorry, time duration can be restricted or can be cut by Gauss pulse or maybe some exponential pulse. In this case, of course, we have we have quasi non-diffraction characteristic, and of course we have decreasing amplitude in time. And coming back to theoretical description, all these results were obtained from Maxwell equation, particularly in wave equation for this restriction. Then wave equations were represented as a Helmholtz equation, and in paraxial wave equation, this is also some simplification of these formulas. In paraxial wave equation, we placed this Airy pulse, and the solution of paraxial wave equation, we have Airy beam that propagate in space in coordinate x and z, or maybe in x and t in time. And you can see the propagation, the not usual, as just usual plane wave. Plane wave is x minus z divided by is x minus z, or the time delay divided by speed of electromagnetic waves. Here we have square formula that give us this self-acceleration and change in position in time. So this is the history of these Airy types. Airy beams, they are studied very good, and they are studied theoretically, and they are created practically too. This is example of that initial function that we state in 0 point. It can be not only like this formula, but it can be represented in such simplified formulas, and still it will exist not so good propagation, not so good result, but it still exists, and it changes the direction in space. And air beam optical oscillator was also discovered and developed. Also, we have near 10 to 20 patents of forming Airy beams in optics, in femtoseconds lasers, and interesting that all patents they prove that it works. And here you can see the propagation distance and deflection main beam from the trajectory. And theoretical results, it's presented by black line, and experimental is presented by dots at some distance, and quadratic feet, it's also present here. So according to quadratic trajectory, this deflection happens. And this is central wavelength of the laser. Okay, so it's real, it can work, and it's interesting. And my colleagues from the Kharkiv National University of Radioelectronics, they have their own theory of electromagnetic waves calculations. It's based on integral equations, not only integral equation, it's Volterra integral equations that do not need boundary conditions, and the initial Airy pulse is presented like this. You can see that phase of this pulse, it changes according to the function in the power of 3, so cubic changing of phase. And the solution of this integral equation is resolvent method. And this resolvent method, it consists of two parts: the field that just meet the boundary while propagation, and another part what happens inside the layer, or inside the inside the layer. And geometry of the problem here in this work, it was studied the interaction Airy pulse with convergent layer. Convergent layer means that the boundaries of this layer, they are changes in time. So it's these boundaries, they are coming to one point in time. And it was analyzed field here in this rectangular, and in these boundaries that are go toward each other in time. And the first field here in the position 0, 0, it has such formula. You can see it's two Airy pulses, one that propagated here and another one that is scattered from the boundaries. While it was obtained the general formula for the electromagnetic strength of electric field that is inside of these M parts. Inside, they are most interesting. And it was analyzed spectrum of this signal. Interesting that Airy pulse, it's ultra-wideband pulses that propagate in space, and they have a lot of energy. And interesting that in the first position, after this pulse come inside the layer, it has such spectrum. And while propagating, this is coordinates of propagating inside this 0, 0 field. It's almost do not change the spectral characteristics. But in the next area 1, we have not only so-called main beams. we have also added scattered from the boundaries signals. And you can see that frequency is increasing in time, and it's become much more wider. This is spectrum that is added from the scattered from boundaries signal. It happens because these boundaries go forward to each other, and this changing in spectrum occur because of Doppler frequency, because these boundaries are moving. And it was very interesting that in the third position, in the area 2.22, we've got not only the spectrum from the first signal scattered from the boundaries, but also we've got the difference between frequencies that are scattered that were in the previous area and from the initial one. And this is like the difference between this spectrum and this one. So this minus this, we've got something in the middle. And this result is already very interesting because it means that such a convergent layer with boundaries that movement to each other, they work as non-linear media that can make changes of frequencies. The next solutions and the next research has to be directed to the making holes in such moving boundaries. And through these holes, we can take some different frequencies. So it's maybe like frequency multiplier in optics or in radioelectronic technologies. So that's all the information. Thank you for your attention. Dear colleague.
Yeah, okay. Thank you very much for your presentation. It was a detailed one. Thank you very much, Simon. If any tricky questions we have in the audience?
Any questions? Can you? So shall we continue?
Yeah, sure.